A rocket requires an immense thrust force to break Earth's gravity. That thrust is produced through a combustion reaction between fuel and oxygen. This conversion of chemical potential into kinetic energy is driven by the microscopic transfer of electrons between atoms. To harness this energy, scientists must determine an element's exact tendency to lose or gain those electrons, a value known as its electrode potential. However, quantifying this value for a single isolated element presents a mechanical obstacle that stops a standard measurement in its tracks. Before predicting the outcome of macro-scale reactions, we first have to solve a microscopic paradox. How do you measure a force that is completely invisible? Consider a basic half cell, a solid metal electrode submerged in an aqueous solution of its ions. Inside, an equilibrium is established. The solid metal and dissolved ions continuously exchange positions, creating an inherent electrical potential. Yet the attached voltmeter registers absolutely nothing. This exposes a core law of electricity. Voltage cannot be measured as an isolated absolute. It is strictly a measurement of the difference in potential between two connected points. We are measuring a single point with a two-point tool. To find any metal's true potential, we must create a universal baseline for comparison. The international scientific community resolved this paradox by engineering a reference point known as the Standard Hydrogen Electrode, or SHE. This chemical reference point functions like sea level in geography, an agreed-upon zero point required to measure all other altitudes. By global consensus, the standard electrode potential for the hydrogen electrode is assigned a value of exactly 0.00 volts. This defines the zero point, a reversible equilibrium where aqueous hydrogen ions and electrons react to form hydrogen gas. By anchoring hydrogen at absolute zero, chemists successfully engineered a universal yardstick capable of measuring the electrical drive of every other element. A universal yardstick is useless if it fluctuates based on its environment. To guarantee consistency, we must enforce 4 strict standard conditions. First, the concentration of ions in the solutions must be exactly 1 moles per cubic decimeter. Second, any gas in the half cell must be maintained at a pressure of exactly 1 atmosphere. Third, the surrounding temperature must be stabilized at exactly 25 degrees Celsius. Finally, a platinum electrode must be used whenever a half cell lacks its own solid conductive metal. Platinum conducts electrons efficiently without participating in the chemical reaction itself. These parameters seal the experiment off from external variables, ensuring that any voltage measured is the result of an element's innate chemical drive. With our zero point established, we can test a new metal by bringing in a zinc half cell. We connect the two systems to form a complete voltaic cell using a connecting wire and a salt bridge. The voltmeter immediately registers a potential difference of 0.76 volts. This non-zero reading indicates that the two systems are out of balance, forcing us to investigate which direction the electrons are actually moving. We can track the physical flow of electrons generated by this potential difference, moving steadily from the zinc toward the platinum. Because it is releasing electrons, the zinc electrode is the negative terminal, or anode. Here, solid zinc undergoes oxidation, releasing zinc ions into solution and shedding 2 electrons. Those electrons are accepted at the standard hydrogen electrode, making it the positive terminal, or cathode. At this cathode, aqueous hydrogen ions undergo reduction to form hydrogen gas. Since the zinc is releasing electrons relative to the 0.0 volt baseline, we append a negative sign to the voltage. This negative sign isn't just a mathematical quirk, it is definitive physical proof of zinc's dominant urge to discard its electrons when faced with hydrogen. By repeating this experiment with every known metal, scientists constructed the electrochemical series, a vertical ranking of elements based on their standard electrode potentials. This series reveals 2 guiding rules, starting with the negative half of the scale. A more negative E0 value indicates a stronger tendency to release electrons, meaning the substance will undergo an oxidation reaction. This eagerness to force electrons onto other elements makes these highly negative metals powerful reducing agents. The second rule governs the positive half of the scale. A more positive E0 value indicates a stronger tendency to accept electrons, resulting in a reduction reaction. This electron-attracting behavior makes these positive elements powerful oxidizing agents. A single scalar value, the standard electrode potential, now serves as a deterministic tool, allowing chemists to predict the winner of any atomic tug-of-war without running the physical experiment. We can test these rules through displacement reactions. Let's start with copper, which has a positive potential of plus 0.34 volts. In our first case, we submerge the copper into a solution of silver nitrate, which has a potential of plus 0.80 volts. Copper's value is more negative than silver's. This means copper is the stronger reducing agent and will force its electrons onto the silver ions. As predicted, copper displaces the silver, dissolving into the solution while solid silver forms. In our second case, we submerge the remaining copper into a solution of magnesium nitrate, which sits at minus 2.38 volts. Here, copper is vastly more positive than magnesium. It has no power to force electrons onto an element that already strongly tends to discard them. In this matchup, copper is the weaker reducing agent, resulting in absolutely no chemical reaction. This dynamic governs the degradation of the built environment, predicting exactly which metals will sacrifice their electrons to oxygen and moisture. By understanding E0, we can engineer sacrificial metals to protect infrastructure from this type of oxidation. The standard electrode potential is a definitive mathematical index, allowing us to quantify the stability of a car chassis and the energy output of a rocket engine before the first atom ever reacts.